So we have discussed two main things. One is how can you make sure there is no loss of information if you are sampling a band limited signal, and the second is if there is no loss of information, how do you reconstruct the original signal? Now, what we are now interested in exploring is what happens if the Nyquist criterion is not satisfied. What happens if omega t by 2 is less than omega m? Or what happens if the signal was not perfectly band limited to begin with, in which case there is no omega m? And intuitively what happens is that higher frequencies that are above the threshold omega t by 2, which is pi by t, radians per second, or one over 2t hertz, higher frequencies above this range, they fold onto the lower frequencies. Which is an operation that is called aliasing. Higher frequencies take the position of lower frequencies. And how do you understand that aliasing operation? We'll again take that example of, let's still work with a perfectly band limited signal. Let's say that this is a band limited signal whose Fourier transform, so you have Ga of t, whose Fourier transform is Ga of j omega. And I'm plotting the Fourier transform Ga of j omega. It's band limited to omega m radians per second. But omega t by 2 is less than omega m. So if I sample it with a frequency that doesn't satisfy the Nyquist criterion, then we always want to take a look at this impulse sample signal Gp of t, which is simply n from minus infinity to infinity, g of n, delta of t minus nt, and we want to take a look at its Fourier transform, because the frequency domain will give us the right information that we are interested in. So the frequency domain expression is 1 over t, you get periodic repetition. We'll do that expression again and again, where the gap between different copies is omega t radians per second. Okay. So if I plot the Fourier transform of Gp of j omega, it looks like this. Of course, you have a one copy with a scale of 1 over t. And that copy ends at omega m and minus omega m. And then you have another copy at omega t and at minus omega t. Now let's look at what does the copy at omega t in this case look like. In this case, since we are not satisfying this criterion, the endpoint of this copy, this should be symmetric. The endpoint of this omega t minus omega m will cross over into your first copy. Right? And similarly, the endpoint of this will cross over into your first copy here also. And where they will cross, this crossing point will be exactly omega t by 2. This crossing point will be minus omega t by 2. Now, if you were to still do the reconstruction using your older method, which is you low pass filter your signal, you low pass filter this GP of t, so your low pass filter will cut off all frequencies from omega t by 2 to minus omega t by 2, and what you will look at is you are looking at the addition of these frequencies. So what you will reconstruct will be something like this. It will go up to this point, then it will go straight. It will go up to this point, and then it will go straight up here. So this is what you will reconstruct. This will be your G hat A of j omega. So this point is pi by t minus pi by t. Okay. So what is happening here, if you graphically look at this figure, what is happening is that around this point, if this is a real valued signal, then this is the Fourier transform is symmetric. So what happens is it is as if this portion of your Fourier transform is folding back around the region around the region of the cutoff frequency. Okay. So it's like you have a version, you have some piece of the frequencies above omega t by over 2 range, and since you cannot measure them, they fold back onto lower frequencies. And while your original frequencies were like this, the red part, what you recover is that you had some frequencies in that region, and some of the higher frequencies have also fallen onto that region, and now you have messed up that region of your frequencies. This operation of the higher frequencies folding onto the lower frequencies is called the aliasing operation, and the folding happens in a very systematic manner. To understand that systematic folding of higher frequencies, we will have to look at signals which are made up of only discrete frequencies. We'll take a look at that, and then we'll understand how the higher frequencies, if you don't satisfy the Nyquist criterion, how they appear in lower regions of the frequencies. So if we consider another shape, so that the phenomenon of folding can be made clear, let's take this case of you have this signal. So this is your Fourier transform, GA of j omega, and then you have a small piece here. So the bandwidth of this is, so this is omega m. Okay. And this point, let's say, is way smaller than omega m. This is much, much smaller than omega m. And your omega t by 2 is some point here. Okay. Now the folding will only be the piece that is outside the omega t by 2 region, and it will fold back inside that region, and your new shape, depending upon what your value of omega t by 2 was, this piece will fold back and maybe appear. This piece will fold back here. This piece will fold back here. So your reconstructed signal frequencies will look like the shape will still be the same, but this piece, the frequency of these pieces will be now much smaller than omega m. So this piece frequencies are smaller than omega t by 2. So what happens after the folding is a function of what your original spectrum looked like. Wherever your frequencies fold, your reconstructed signal will have those frequencies plus whatever was present before. In the previous case, you had frequencies present in the region of folding. In this case, you don't have any frequencies present in the region of folding. Now, understanding the aliasing with these continuous spectrums can be a little challenging. So let's take a look at the case of discrete frequencies, signals consisting of just sinusoids, and see what happens with this aliasing phenomenon. So this is example 3.18. We had previously looked at a similar version of this just in theory. So we are given three sinusoids, G1 of t, which is a 3 Hertz cosine, then Gt2 of t, which is a 7 Hertz cosine, and G3 of t, which is a 13 Hertz cosine. Yeah. But all of them are sampled at t equal to 0.1 seconds, which is that the sampling frequency is 10 Hertz. So among these three signals, if we sample them and compute G1 of n, G2 of n, and G3 of n, we sample all three frequencies with a sampling frequency of 10 Hertz. Which of these sinusoids will be perfectly preserved and which one will undergo aliasing? So according to the Nyquist criterion, this G1 of t will be perfectly preserved after sampling because it's smaller than 5 Hertz, which is half the sampling frequency. Both G2 and G3 will undergo aliasing. So the question is, we started with 7 Hertz and 13 Hertz frequencies. Where will those frequencies end up? Where will the folding happen? That's the phenomenon we want to understand. So to understand that, we'll look at the frequency domains. The Fourier transform of a cosine, of course, is just two impulses at the locations of the frequencies. So this is the Fourier transform of this 3 Hertz cosine. Similarly, we have omega minus 14 pi plus delta omega plus 14 pi for the 7 Hertz. Then we have delta of omega minus 13 pi, 26 pi plus delta of omega plus 26 pi for the 13 Hertz. We want to understand the folding phenomenon, and to understand that phenomenon better, we'll look at again that periodic repetition expression that we have been working with. Okay, so this is the case of the first sinusoid. This is your Fourier transform of your original sinusoid. And then this is the Fourier transform of your impulse sample signal. You first get a main copy of your Fourier transform around 0. Then your sampling frequency omega t is 2 pi times f of s, so which is 20 pi. Right? So you get another copy around 20 pi and another copy around minus 20 pi. Now this impulse location of this is 20 pi minus 6 pi, which is 14 pi, whereas your sampling rate is pi by t, which is 10 pi. Right? So if you low pass filter from minus 10 pi to 10 pi, you see that we sample out all the other copies. The impulses don't fall within the minus 10 pi to 10 pi region, and will recover the original signal. So if we low pass filter this with cutoff of 10 pi, then we'll recover the original signal G1 of t. There is no aliasing. So this we already know. We realized the fact that the frequency was 3 Hertz. There will be no aliasing up to 5 Hertz. So there is no surprise here. But now let's look at the other two frequencies which will alias. So we'll have to pay attention to the different values. Again, we have the same thing, that omega c, this is 10 pi, the cutoff frequency of and minus 10 pi. Now you get one copy. This is your first copy of your spectrum around 0, and then you get another copy. You get the first copy of your spectrum, which is this is 14 pi, and this is minus 14 pi. So the first copy is outside the 10 pi and minus 10 pi region. This is your main copy. This is due to the spectrum around 0. Okay. Now you have another copy due to the spectrum around 20 pi. Now where will be the endpoints of that spectrum? This endpoint will be 20 pi minus 14 pi, which is equal to 6 pi. So it will actually fall within your low pass filter region. So this is like, this was your true frequency. This was your true frequency, and this is like it folded onto a lower frequency. The folding phenomenon is happening because of the copy at 20 pi region. Okay. And similarly, you have a copy at minus 20 pi. So this is your copy at minus 20 pi. And this endpoint will be minus 20 pi plus 14 pi. That's equal to 6 pi. So this red part again was your main copy, and it is as if it folded onto minus 6 pi region. Now if I low pass filter this picture, what I get is an impulse at minus 6 pi and an impulse at 6 pi, which corresponds to which frequency? It corresponds to the 3 Hertz frequency. So the reconstruction of this will be actually cosine of 6 pi t. So your 14 Hertz frequency has folded onto, sorry, your 7 Hertz frequency has folded onto a 3 Hertz frequency, because you did not satisfy the Nyquist criterion. Okay. One single frequency, it was present at 7 Hertz, it's now appearing at 3 Hertz. Let's do that same thing for the final sinusoid of 13 Hertz. So now the first main copy that we will get is due to the copy around 0, and this is what the original frequencies are: minus 26 pi and 26 pi. Okay. Now there will be a second copy around 20 pi, and the left endmost point of that 20 pi will be 20 pi minus 26 pi. Actually, that will be here. So this is 20 pi minus 26 pi equals minus 6 pi. So this version that is appearing here is actually a folded version of this frequency, and it has folded so much that it has gone onto the negative side. Okay. And similarly, there will be a copy at minus 20 pi, and the rightmost side of that copy will be minus 20 pi plus 26 pi. That will appear here. So this is going to be minus 20 pi plus 26 pi equals to 6 pi. And now when you low pass filter it from minus 10 pi to 10 pi, you are still going to recover what you will get after low pass filtering is an impulse at minus 6 pi and an impulse at 6 pi. And this corresponds to a cosine of 3 Hertz. So even this frequency of 13 Hertz will fold on to 3 Hertz frequencies. So we looked at two signals. One was a 7 Hertz frequency, one was a 13 Hertz frequency, and they both folded onto the frequency of 3 Hertz. Okay. So in general, if you want to figure out where the frequencies will map to, there is a simple formulation which is shown through this plot. Say you plot your input frequencies on the x-axis and your output frequencies on the y-axis, and your sampling frequency is omega t. If your sampling frequency is omega t, then we know that we cannot reconstruct any frequency that is above omega t by 2. So your output frequencies will always be limited to omega t by 2. Your input frequencies can be as large as you want. Your output frequencies will always be limited to omega t by 2. Okay? And you can express the input-output relation in terms of this kind of a plot. Up to omega t by 2 of input frequencies, you always recover the frequency that you started with. But if you go above omega t by 2, then actually instead of recovering a higher frequency, you start going down. So much that actually if you had a frequency of omega t as the input, your recovered frequency will be 0. Now if you go even above that range, you will again start going up. And this will be the point of 3 omega t by 2. And this thing just repeats itself. This will be 2 omega t and so forth. Okay. This repeats itself, and if you look at, for example, our original version, we had a frequency of 3 Hertz which fell up at this point within this region, so we recovered 3 Hertz. Then we had a frequency of 7 Hertz which was between 5 Hertz and 10 Hertz, so you still recovered the same frequency. And then we had a frequency of 13 hertz, which was between 10 hertz and 15 hertz, and we still recovered the 3 hertz frequency. That is, if you just do this plot, you'll figure out why we were getting 3 hertz all the time. Now you can ask the same question about negative frequencies. This plot is really useful if you are dealing with real valued signals, because in real valued signals, the frequencies, the negative and positive frequencies, you have a symmetric spectrum in the Fourier domain. But if you are only dealing with negative frequencies, you get similar kind of a plot. The only thing that will change is that you will have just a reflection of this plot. So these are your output frequencies, input frequencies. Minus omega t by 2, minus omega t, minus 3 omega t by 2, and minus 2 omega t, and so forth. And these are your output frequencies. So the maximum output frequency in the negative, on the negative side, will also be minus omega t by 2. And it's the same plot up to minus omega t by 2. You get back the original frequency. But after that, you get back a lower frequency with a linear relationship with a slope of 1. Then you go back up again. And then you go down again, and this keeps on repeating if you have only negative frequencies. So we can take examples of some simple cases to clarify this. Let's take the example of sampling frequency equals 15 kilohertz. And let's say my input signal is to an LTI, to just a analog to discrete, and then I do discrete to analog again, right? So my input signal is, let's say, 28,000 times pi of t. So if I pass this input signal through an ideal continuous to discrete, and then immediately do a discrete to continuous with the same time period, the question is, what is the output, x hat of t? So the frequency of my input signal is, so input frequency is 14 kilohertz. Which means that we will have aliasing because this region is 7.5 kilohertz. So we have no aliasing up to 7.5 kilohertz. So we'll have aliasing, and the output frequency, we are below this region. So this point is 15 kilohertz. Our input frequency is 14 kilohertz. So what is the output frequency going to be then? So I will have aliasing with my x hat of t will have output frequency. This is going to be 1 kilohertz. 1 kilohertz output frequency. And similarly, if you are given any other frequency, input frequency, you can just use this plot to figure out what will your output frequency be. This is assuming that you are doing perfect sampling, perfect reconstruction with the ideal reconstruction filter, and that sampling time is the same in both cases. So there are two main lessons that you want to take from the concept of aliasing. Number one is that aliasing introduces new frequencies in the signal that were never present there. So in the above example, the input signal had a frequency of 14 kilohertz, but what you are getting out is a frequency of 1 kilohertz. But that is not the only issue that aliasing creates. If you already had a frequency at 1 kilohertz present in your signal, then, and if both those frequencies have the same phases, then at the output you are going to get twice the amount of frequency that you had originally present in the signal. So the other effect is that aliasing corrupts low frequencies onto which the higher frequencies map. So because of this, aliasing is a phenomenon that should be avoided as much as possible. So aliasing, the bottom line is bad and should be avoided now. Of course, one way of avoiding aliasing is that you sample at a high enough rate. But many times that is not possible. For example, if you are trying to record someone's speech and there is background noise, while you know that the speech is band limited to 3.5 kilohertz, if there is background noise, that could go up to 15, 20, maybe even higher. Right? So if there is background noise that, let's say, 15 kilohertz, just because of the background noise, you don't want to sample at 30 kilohertz. So avoiding aliasing by simply increasing the sampling rate is not always desirable. So what is the other option that is available to us? Say the sampling frequency is omega t radians per second, and you don't know the input signal that you are getting, you don't know that whether it is band limited to omega t by 2 or not. So we cannot guarantee that the input signal is band limited to omega t by 2 radians per second. So then how do we ensure that no aliasing happens? So to do that, what we can do is pass the signal This is your input signal. We pass it through a continuous time low pass filter. And what should be the cutoff of this filter? With cutoff frequency omega c equals to omega t by 2. Because when you do that, you will get back an output that is guaranteed to be band limited to omega t by 2. So we already saw a notion of a low pass filter with a cutoff of omega t by 2. That came up in the discussion of reconstruction filter. A reconstruction filter which takes your samples and converts it into a continuous time signal, that also has a cutoff of omega t by 2. Okay. But that low pass filter which is put at the reconstruction side, and also the scaling of that filter is taken to be capital T. In reconstruction filter, the scaling is taken to be capital T. In this filter, we don't want to mess with the amplitude of your original signal's frequencies. So this filter which is put up at the start before your sampling process and has a cutoff of omega t by 2, this is called anti-aliasing filter. Okay. It's just a specific name to describe. They are all low. Reconstruction filter is a low pass filter. Anti-aliasing filter is a low pass filter. We give them, they both have the cutoff ideally of omega t over 2. We give them different names to specify where they exist in our signal processing chain. If the low pass filter exists before the sampling operation, it serves the purpose of killing higher frequencies so that you don't have aliasing. We call it the anti-aliasing filter. So anti-aliasing filter, the frequency response of that is 1 for omega less than or equal to omega t by 2 and 0 otherwise. Again, we are assuming an ideal setting. And the impulse response of that is HAA of t. So it is 1 over t sine of pi t over capital T over pi t over capital T. So sine pi t over capital T divided by pi t. Okay. It's exactly like the reconstruction filter, except that this value is, instead of 1, this is capital T. The goal of the reconstruction filter, the goal of the anti-aliasing filter is simply to remove frequencies higher than omega t by 2. It does not try to change the contribution of frequencies below that range. And in some cases, anti-aliasing filter will lead to loss of information because you are throwing away higher frequencies. But at least you are not making those higher frequencies fold onto lower frequencies. And anti-aliasing filter, as I said, is in almost all practical systems, because you cannot ensure almost all practical systems have an anti-aliasing filter before you do the sampling operation. Even if you are guaranteed that the input signal is approximately band limited. You put an anti-aliasing filter to avoid any confusions about there may be some spurious high frequencies present. So an anti-aliasing filter always precedes the sampling operation.